Yeah,
Bridge
the
boards.
Ace Bridge.
Do you have any of those?
I do,
Those
and I'm getting
boards.
more on Saturday,
Okay,
so I can use them.
sweet. I just need one.
Right.
Thanks, dude.
Yeah, I have one extra at my house right now, so maybe, yeah, like Sunday or something.
Is Lorena back?
Hmm?
Is Lorena back?
She won't be back until March 13th, at least.
I'm just trying to locate parts where I can, yeah.
Gotcha.
Why, you need to order something?
I ordered something, it's like stuck in, you got that mail, right?
Yeah.
Uh,
I mean, you can do what
I just
Nat's
bought
doing,
it.
just bought and seek reimbursement later.
No, I like purchase, I will order like 2-3 matrix feeders, but everything also needs one, right?
Mhm.
Yeah, if you have an extra, I'd love to use it.
It's like, if the order gets through, yeah.
Yeah.
Okay, I think we have a reasonable quorum, so we'll start? Okay, let's do it. Okay, my turn to listen. Okay, well, let's go.
Okay, hi everyone. So my name is Juan Carlo, but I just go by Carlo. My partner is Jeannie, and the project we're working on, we're calling it Project Lo-Fi for now. So what is Project Lo-Fi? There's a high-level diagram here in the upper right corner to give you an idea of how we expect for it to go. In short, it is a mood and activity augmented music recommendation system. So how we intend for it to work is using the Hexaware, you can take heart rate measurements, which can be used to estimate a user's mood. And by taking accelerometer information from a user's smartphone, you can use that to estimate what activity they're doing. And using that along with more traditional inputs to a recommendation system, like user preferences, we'd be able to hopefully suggest a highly personal playlist to a user generated from them just living their daily lives. So the main benefits we hope to get from it are in terms of mental health, in the ability to reduce stress and make things more manageable, and also in terms of physical health by making experiences like jogging and other kinds of exercise more enjoyable and more doable for a lot of people. Specifically, one of the first cases we're trying to implement is to try and improve the experience while jogging. So music can evoke a sort of distraction effect that can make it easier for you to zone out during, say, like longer cardio sessions and make it easier for you to run more in time and just keep up a good pace. And we also just want to be able to generally like improve your mood in daily life by like suggesting music that will hopefully help you feel better at different times. So as for the technical aspects of it, one of the first questions we naturally had to ask when we started this project was, how do you quantify something as intangible as like mood, something that's can be hard to put numbers to? So in 1992, this two-dimensional representation of mood called the valence arousal space was first introduced, and it's been used in a lot of literature since. And this two-dimensional representation works like this. So the horizontal axis is called the valence axis, and farther to the right are more positive emotions, and farther to the left are more negative emotions. And the vertical arousal axis, the higher up on that axis is higher energy emotions, and the farther down is lower energy emotions. So Deezer, which is a music streaming service, they published a paper last year on mood classification of music, and in it, they created this data set of 3,514 songs, which all had valence arousal values that could be mapped to the valence arousal space. You can't see the song titles here, but it looks something like this. This is actually an actual plot of some of the songs. And for example, one of the samples from the set is a song called The Bleeding by Five Finger Death Punch. And you don't need to have heard the song to be able to guess that it's probably a pretty angry song. And it's appropriately plotted in the angry quadrant of the valence arousal space. So taking that into account, there's a paper published in 2009 showing that you can map heart rate variability to a point in the valence arousal space. So using that as a means to estimate a user's mood. So then what we plan to do is use that through the hexaware, estimate where the user's mood is in this plane, and recommend songs that are close to it. So that covers the connection between mood and music recommendations. So what about activity? So the first case we're looking at is if we can tell that the user is jogging, how can we recommend better music to them? So what we're planning to do is to detect the user's cadence, which is like their stride rate, or the rate at which they're jogging, and find music with a matching tempo. So if you've ever jogged to music and you found that by chance the song you're jogging to syncs up perfectly with the rate that you're stepping at, it feels really good. It's a good driving force, and it might even make you want to go beyond your comfort level in a good and safe way. So that's something we want to try and implement here. So the way we're doing that is we trained a one-dimensional convolutional neural network to be able to distinguish between 6 different kinds of activities. Using this data set published by Fordham University, here are some windows of what different activities like jogging and walking and sitting would look like. So what we're able to do was, by training a network, we were able to get a CNN with 99% classification accuracy, distinguishing between 6 activity types. The confusion matrix is there. And by using this other data set with tempo information on different songs, we're able to append all the songs in the Deezer data set with a 3rd dimension, which is tempo. And we are able to lift that 2D representation into 3D here. That's what that looks like. So then based on what cadence people have as they jog, we can recommend songs based on tempo as well. So that's some of the stuff that we have done so far, and what we have to do still is we have to implement sending the heart rate data and cadence data from the hexaware to the Android. And we need to put the model on the phone to make sure that the practical accuracy of this is as good as the test results promise. And we also have to finish implementing the Android app. And that's our presentation. Thank you for listening.
Perfect. Exactly in time. So Tyler, you're next.
Hi everyone, my name's Tyler, and my project is about splitting ML models between embedded devices on the edge and the cloud. And so the motivation behind this is that embedded devices, they're often low power and low speed, not always the case, but often. And when you're trying to make inferences, you want to be able to do this relatively quickly. You want your results fast, so you want low latency, but at the same time you don't want to be sacrificing battery life, as that means you're going to need to maintain these devices more often, or it could increase their cost by needing larger batteries, something of that sort. And so you're able to take advantage of cloud compute by splitting your model between your node that you have in the cloud. And so the status quo sort of is to, for instance, you're using Siri on your device or something, a lot of the time you just take the inputs, ship them off, get them back with your result. But in situations where you've got a slow network connection, sending over an image or an audio snippet can actually take a considerable amount of time, sometimes even longer if you've got, for instance, a smartphone, longer than just doing the computation on your own device. And so you have to be careful with where you're going to be splitting your model. If you split it too soon, then it's possible that you're sending too much data over the network, incurring a lot of overhead there and power usage. But if you split it too late, then you're doing too much computation on your own device, which, once again, too much power usage, too slow. And so my goal for this project is there's a number of new platforms that are coming out. So we're past the point where the only option is a standard microcontroller, and we're starting to get into, there's now embedded chips specifically for inference. And so my goal in this project is to look at some devices of that type and get a bit of an understanding of how long things actually take to compute on these new chips, figure out how large these intermediate layers are, how much of an impact communication has, and if possible, it'd be interesting to find out how much energy this actually uses, because these platforms claim to be highly optimized. And so what I've done so far, the first step was to settle on platforms. I settled on 3 main platforms. One of them is just a standard microcontroller. That's the one on the bottom. That's the board we've got for this class. It's based on an ARM IM processor, I believe. And then so we've also got the GAP8. The GAP8 is a RISC-V design, and what makes it unique is it's got this 8-core multiprocessor, parallel processor thing that they've designed to do computations along these lines, machine learning inference. And they claim low power, high speed. And then the first option here, the Raspberry Pi 3 Model B, and what's interesting is actually that Intel Neural Compute Stick. It's a device that takes the form factor of a flash drive, you stick it into the USB port on your Raspberry Pi, and it accelerates computation. And I believe you're able to buy the chip inside of that compute stick on its own to slap onto your device. And so those are the 3 platforms that I want to look at. And so each of these platforms is different in its capabilities. You've got the microcontroller, which just does standard boring ARM computations. You've then got the GAP8, which they're open with how it works. And you've also got the Intel Neural Compute Stick, which as far as I can tell, they don't really elaborate too much on the secret sauce that goes into how it works, so I could be wrong there. And so as a complication factor, each board and each technology is programmed in a different way, but I found out that there are ways for each platform to port a pre-trained TensorFlow model onto that particular platform. So I'm planning to use TensorFlow in order to have a single model that I can run everywhere and assume that the model overhead is going to be the same. I've also looked into data sets that could be reasonably run on devices of this size. And it seems that just looking at examples and such, that CIFAR10 and MNIST are pretty safe. MNIST is handwritten digit recognition, small 28 by 28 images, and CIFAR10 is real small images, and there's only 10 classes. So that's what I've done so far, basically looked into this, done some background work.
Are you planning to store the data set on these things, or just somehow?
Right. So what I was planning on doing is I decided I don't need the whole data set on there, because reasonably one unique thing about machine learning in an embedded context is when you're doing bulk processing, you can use a GPU, a TPU, something like that. But with inference on the edge, you're just going to be doing one sample at a time, right, typically.
So are you arranging to feed the sample at a time? Because that would be the real...
Right. So I'm not planning on fitting in more than one image at a time necessarily. My main concern was really the weights that would be required for the model, because some of these, I believe the microcontroller, the ST Nucleo board has 0.5 MB of flash, perhaps, which isn't much at all. So considering how large some models can get. And so then my next steps now are I want to settle first on a model and a data set to use. And since I'm going to be using TensorFlow, I'm hoping that the architecture should be able to be kept consistent and not run into any memory issues. After settling on that, I want to port it, which hopefully should be simple. Where I see difficulties potentially coming in is instrumenting the models and adding the splits into these different models due to the nature of the different porting tools all working differently. And then lastly, I want to add in the functionality to send the results to the desktop for computation. And from there, I can start taking different measurements. I don't think the measurement taking should be too difficult, with the big difficulty being more in setting up all the instrumentation.
Great, thanks.
Hi everyone, have you ever been to the Westfield parking lot?
Yeah, it's horrible.
gigantic, right? Without a map or without anything like a guidance system, you will never ever find your car once you park it and leave, right? So our project might give you a hand on it. So we were planning on using the latest Android P Wi-Fi RTT API. It was just released last year in May. And our hardware base is a Pixel 3 phone, basically a Android phone. And more like we need a Wi-Fi RTT protocol supported device. So in this case, we have found two of them. One is the Google Wi-Fi and one is the Wild. This is a company from Israel. It was pretty pricey, but we got that covered for us. So our first goal was basically to find the ranging and the localization accuracy of those two devices using our application. So the ranging basically means if I'm connecting my device to that router, how long will the distance measured compare to the actual distance? And the localization would be with a whole system established, how would the accuracy be if I'm actually standing in the range of detection? So our next goal is to implement a product based on the system, basically trying to find yourself in a parking lot with your car. And in this way, you would not have the hustle when there's no GPS signals or no cellular. You wouldn't know where you are on Google Maps or on anything like that. So just a quick layout of the process. We have our Pixel phone and two of the APs. So we scan and request the first to recognize if we're in the system or not, and then we get that acknowledgement. So the connection is established. Then a fine time measurement signal was sent to that device, and we also get an acknowledgement for that. So from that time of travel, we will be able to calculate our distance to one of
What does
the APs.
FTM mean?
Fine time measurement.
Fine.
Yeah. So how do we evaluate our process? So I've already talked about ranging position and also localization. So these are the two main features or two main objectives that we're shooting for. And the environment could also different our results. So like something like temperature, that's weather, whether we're in an indoor parking lot or in an outdoor parking lot, whether we have a lot of traffic or a lot of cars parking in that parking lot or not, whether we have the antenna oriented around us or in a single direction, all of those things could affect our results. So this is just a list of the type of scenarios that we will examine in. So the basic idea, again, is to record our location right next to the car. So the user first park the car, take out their phone, record the location, and then just go out, do some shopping or eating, and then once they step back into the parking lot, then turn on the app and just try to find your car
Why
over
can
there.
you not detect that I stopped driving and I parked?
Because
Like, why do I need to do the first step at all?
That's because well, you have to keep your app on the whole time if you want to do that.
It's sitting in the background, no?
Well, you have to turn it on. Like you can turn it
Okay,
on
so let's
after
say
you
I just
park
turn
your
it
car.
on, right? Because
Right.
you can, because Android gives you transportation modality, so you
Mhm.
can detect driving to walking transition,
Mhm.
and then just do
Yeah,
this
that's a
thing on
good
your
point
own.
too. Yeah, we might. Okay.
And one thing, just briefly going off of that, I know that the Westfield Mall
Mhm.
tracks where you parked based on
Yeah.
license plates?
I've seen that. I've actually used it, but it was very crappy.
Yeah, but just
Yeah.
like theoretically, in the cloud, it
Mm-hmm.
hook your account to your plate and
Yeah.
automatically.
Yeah, they do that, but there are other type of options, and this indoor localization also works in other places. If in a shopping mall, like if you're going to a shopping mall for the first time, you wouldn't like you can read a paper map, but yeah, you have other options. So our initial results is basically we have already implemented this system, and we actually have built our app. It's just listing your distance in meters and RSSI values in decibel per meter. And once I tap that record, it will locate my current location, meaning my car. So and after that, we just walk around and try to see how would that location change, basically. So yeah, I think that's it. Thank you. Thanks.
Okay.
Okay, so the title of this project is Distributed Modulation Classification. Okay, so the idea is the following. Mobile operators pay billions of dollars to have access to the spectrum, right? But the thing now is using $100 software-defined radio, you're able to access this licensed spectrum. So let's say this user is in red, the colors are not showing correctly. So these two users are in red, right? These users are using the mobile operator network and they're paying their fees. But these two users could be using a software-defined radio and illegally using the spectrum, okay? So these users will affect the legitimate users of the operator. So that's going to be a problem. And it's going to be a problem that's hard for the operator to detect because these two users can be talking directly using low power. So it would be hard for the operator using the base station that's far away to sense it and to do something about it. So what's the solution for this? You need to have distributed radios that monitor the spectrum. So these are these small devices. And the idea here is you're going to need many of these devices since they have to be spread everywhere, unlike the base station. So they would be able to detect illegitimate use of the spectrum, okay? So now the question is, what should you monitor? A simple criteria you can monitor is the type of signal. So let's say if you're using GSM, you're expecting a certain type of modulation only. If you found someone using another type of modulation, then this someone is not a legitimate user of the spectrum, and you need to do something about it, okay? The simplest solution is to jam them, to see when they're transmitting using a signal that's not expected using the standard, you're going to go ahead and jam them, okay? So you need to detect them in a timely manner to be able to take action against them. Okay. So this is the idea of the project. I'm going to have some sensors, which is made of software-defined radio, a low-cost one, plus a Raspberry Pi. And this sensor would be connected to a cloud device. The cloud device would be powerful, would have a real computer with a lot of RAM with a GPU. And you have some link between this sensor and the cloud device, okay? So now the first step is you want to run modulation recognition. You want to know what kind of signal they're transmitting. But here you have many challenges. So the first one, so let's say if you want to run your modulation recognition algorithm on the sensor device, on the Raspberry Pi, it's going to take you 10 milliseconds. If you run it on the powerful computer, it's going to take you 1 millisecond. So the question, what is the better option, to run it on the sensor or on the cloud? Everyone would think it's on the cloud, but there is a trick here. If you want to run the recognition on the cloud, you'll have to send all the data through this link, right? So maybe it will take 10 milliseconds here, 1 millisecond here, and transferring the data can take a lot of time, can take, let's say, 20 milliseconds. So in this case, it would be better to run the recognition on the sensor device directly, okay? and can be somewhere in the middle. Maybe it would be better to do some processing on the sensor device, reduce the amount of data that needs to be sent, so that you're minimizing the total delay until you recognize the type of recognition. So that's the first challenge, is latency, okay? The second challenge is rate. Because let's say if you're detecting 10 transmissions per second, you need to process them using 10 seconds, right? Else your system won't be able to keep up with the whole thing. So you need to take into account the rate of at which the sensor device can process data, the rate at which this link can send data, and the rate at which the cloud can process the data, okay? There is also another parameter, the accuracy of the recognition. Eventually, if you're going to run it on the sensor device, you won't be able to use floating point calculations because it will be too expensive, right? So you're going to need to have some approximation here. So the more you run the data, the processing on the sensor, the lower accuracy you get. So this is another thing you need to take into consideration. So the problem is as follows. Given the link is able to support a certain capacity, and the sensor node is able to process data at a certain rate, and the cloud is able to process at a certain rate, you want to find the solution that maximize the accuracy of the recognition, okay? So you need to find what kind of distributed algorithm that would run here and here, and would give you the highest accuracy given the system described, okay? The second problem you have is this system is dynamic. Like the link, if you're using Wi-Fi, it's affected by neighboring nodes, anyone who's transmitting. So sometimes this link can be active, sometimes it can be idle. So yeah, so its rate would be variable. Also, the number of packets that your sensor is detecting can also change. Okay, so you need to have a system that's able to adapt to all these variables.
Your algorithms need GPU because they are neural network, or is it like what kind of how do you detect the modulation? I guess what kind of algorithm?
Yes, I'm using deep neural networks.
Oh, okay.
Okay. So like I said, I'm using deep learning. So like I said, the system has to be adaptive. Okay, so I need to monitor rates, delays, and have several neural network architectures that where parts of the neural network would run on the sensor and parts would run on the GPU. Okay, and each model would get narrower, and the narrower it gets, the less data it needs to transfer. Okay. So the idea is I'll have several architecture and I'll compare how much delay do they need, how much performance do they give, okay? And then I'm going to benchmark them on the hardware, and then I'm going to build a controller that will always keep track of how busy is this link, how many packets I'm detecting, and how busy is the cloud computer, and based on this, it's going to choose one of the set of algorithms or the set of neural network architecture that I will develop. Okay. So the progress so far is I surveyed modulation classification. Like in the literature, there are several architecture and many analyses of how different parameters affect the accuracy of modulation classification. I started reading about neural network quantization because eventually I'll have to do that to run it on the Raspberry Pi. The most similar work, it runs modulation classification entirely on Raspberry Pis, not distributed. That's the closest thing that I found. So far, I already done the setup for the Raspberry Pi. I forgot to say here that I'm going to use a Pluto SDR and Raspberry Pi 3. So I already configured the Raspberry Pi to work with Pluto. I installed TensorFlow on the Raspberry Pi and on my computer. I set up the Wi-Fi and Ethernet. I did some initial evaluation, like I got a modulation classification dataset from the internet, and I evaluated a Bayesian convolution network on my computer, okay? So the next step, I'll start exploring different architecture to see how the quantization affects them. Then I'll start evaluating this different architecture on the hardware in order to have several possible solutions. Then I'll build a controller that would monitor the status of the environment and based on which choose the algorithm.
So what kind of modulation schemes are you trying to classify? Like, are these standard Wi-Fi Bluetooth type things? What band? So this is what the Pluto goes to, what, 2.4 gigahertz?
Yes. So I'm going probably to use the 900 megahertz band because it's empty.
Okay.
I'm going to use just I'm not going to use any specific standard. I'll just use simply modulated signals. Just generate random bits and
Okay.
with a given modulation, digital modulation, and just see if it will get it correctly or not. Okay. Thank you.
Hi everybody. I'm working with Seraphine on a project, and we're just basically doing embedded AI on Mbed, but we're doing more than just that. So in our project, our overall project goal is to get basically a library or API that developers could use to like implement neural networks on embedded systems, and probably through Mbed. So basically, like a lot of embedded systems, such as like Hexaware, there's a lot of sensors on them that you want to use and incorporate into your neural network, and it can be difficult to like do so if you don't have like an API to do it. So that's basically what we're creating. So our specific goals, we just want to create the library that first off generates a neural network, and then it would put it on the embedded platform. So we're thinking of doing either the STM board or Hexaware. Hexaware is kind of more interesting because it has more sensors. And then one thing that we could do is just use the library that we create to create like a pretty simple like test neural network that we would just put on the board and it would work. So our technical approach, pretty basic. There's a flowchart over there. Basically, the user gathers a bunch of data from something like Hexaware. You could use it to classify and train a neural network to like do like a physical like a motion sensing kind of thing, and you do that on like a desktop or like a good computer using either TensorFlow or Caffe, and then you would convert the full neural network, and then you would kind of shrink it down to as little as possible into like a C++ code, and then which you would just put it onto the embedded system using Mbed. And currently, so we're learning how to implement neural networks onto like either the STM board that we have or the Hexaware. So we've looked at, for STM, there's the 32Cube AI. Basically, it takes a neural network from Caffe, and it shrinks it down and makes it so you can run it off the STM board. And there's two other ones for Hexaware, basically for ARM, the M core, the Cortex M cores. You have CMSIS-NN, which is like the neural network. Basically, it does something similar, and people have been using it to implement like various neural networks. But another interesting one that we saw was uTensor or microtensor, and it's like intended to work with Mbed. It basically creates the C++ code for you, and then it's a pretty streamlined process. But in this one with microtensor, there was a project where they had like a camera, and it could recognize pictures after training it off of a data set with like good accuracy and fairly good time. And they were doing it on like a Cortex M core, which is why we're interested in that, because the Hexaware has a Cortex M core, which is a bit less powerful, I think, than other processors. So, and after we do all this testing, then we're gonna decide what platform to target and then create the API. So you can hook up like a neural network to all the sensors and like get some output. And this is basically for like edge computation rather than kicking out to the cloud. And so you can just do it on the device itself. Yeah, that's basically it.
Okay.
Hi, I'm Shipin. So our group is going to use Hexaware to be like a mouse to control the mouse movement. So our project is like use different hand movement to like to control the mouse, like moving X, Y direction, or it's like clicking it or scrolling it down or up, something like that. We also decided to use machine learning for the hand movements to like determine which kind of action that is going to take. And also, the mouse movement instruction will be transmitted through the Bluetooth to the computer. So what we need to do is collect and label the data for the mouse movement. And also we decided to use both the regression and also classification. So we are going to use linear regression for like determining the movement in the X, Y direction in the display. But we are going to use the classification for scrolling and also the clicking action. So the current data is like we are still working on collecting the raw data. The problem is that since the accelerometer also contains the gravitational force on it, and we need to, and because it's moving, it's difficult like to get the linear acceleration. So we are considering to use a filter to get the linear acceleration. And also we have the problem about like, since we are getting data from the hardware through the USB, but we also like check the actual mouse movement in like through the Python in the computer, since there's a different time stamp between these two. So we need to figure out like during what time is actually moving that much. And at first we tried to use the Arduino to pair with the hardware, but we failed, so we decided to go with the Raspberry Pi. Yeah, that's it.
Okay, great.
Hello everyone, my name is Ray, and my project is a wireless leash. I don't know about you guys, but I jog a lot, but I don't like using treadmill, so I tend to go outside. But there's one thing I don't like. I kind of have to carry a water bottle with me, but that creates kind of imbalance in the movement. So I either choose jog happily but dehydrate, or either choose hydrate but jog kind of awkwardly. So I kind of want to do this project for a long time. It's a wireless leash. So basically, I can create a robot that follow me, and I can put a water bottle on there, so I can jog freely and just a robot carry water with me. So that's that's my primary intention. So I can create a robot where it can carry water with me without any specialized like beacons or router to actually localize the position of me and the relative location of the robot. So given the time that I have, so I'm thinking I'm setting out a relatively simple environment assumption. So it's going to be outdoor, so no other Wi-Fi support or other router or any other support unit I can use, but it's just gonna be a flat floor like a basketball court or tennis court, so no other obstacle in the way. And but of course in the future, if I want to add some more sensor, I probably can avoid the obstacle in the way. So that's a primary goal. And method I'm then using is I'm using Matrix Creator, which have 8 microphones, and I can use a beamforming to detect the direction of the sound coming. And I can use iPhone to send a very low frequency sound, so big. And I think human ear can only hear frequency from 20 Hz to 20 kilohertz. And based on my personal experience, I can only hear anything above 200. So anything below 200 is fine, or anything above 15K is fine, but the sample rate of the Matrix Creator is not high enough, so I decided to use low frequency. And I found a library that support Linux or support that can use on Raspberry Pi, which is called ODAS. It's called Open Embedded Audition System, which you can detect, you can measure the direction of arrival of the sound. So I'm gonna use that to measure the direction detection. And for distance detection, I initially think of two-way ones using Bluetooth or Z-Wave to timestamp the current output frequency. So the iPhone is gonna output frequency that change with time. For example, it changed at time equals 0, it output 80 hertz frequency. At t equal 5, it output 100 frequency. And then the measure creator will receive the timestamp of the frequency through Bluetooth, and then you can use FFT to measure the current receiving frequency, and then measure time difference. So then you can measure the relative distance between the user and the robot. But based on the lecture, I think I don't think. Although Zigbee Z-Wave is pretty nice, but iPhone didn't support Z-Wave, so I have to use a BLE. But I think Bluetooth is not really accurate in terms of time stamping. So and on the other side, I think the absolute distance between me and the robot is not really important. I just need to measure like a relative distance. So I think probably using the simple geometric estimation of the distance should be fine, since the ODAS library already give me the direction, three-dimensional space of the degree of the direction of arrival of the sound. So I think that should be sufficient to estimate the relative distance. And as long as the robot is not too far away from me, I think the project should be considered a success. And here's the current status and problem. I think I found all the necessary library I need to use. ODAS is the library that could detect the direction of the arrival sound I mentioned before. And Matrix Creator have a built-in finite impulse response filter, so I can filter out the sound to only limit it to low frequency sound. But the problem that I found is, well, the first one I already mentioned. iPhone didn't have Zigbee, so I have to use BLE for timestamp, and that's not a good timestamping method. And the second one is Raspberry Pi Zero. It's a little bit too slow for ODAS, so I'm planning to get a Raspberry Pi 3, since that's their recommendation. And that's about it.
Great.
Oops, oh, that's a credit.
I think just focus. Okay. All right, cool. So this is convenient going right after Ray, because ours is kind of similar, but we do have some differences too. So yeah, we want to do a Google Assistant self-driving robot. So our project goal is to basically create a robot that has all of the services that Google Assistant has. So if you guys have a Google Home or Alexa, it'd do that, and then it also has some custom functionality to drive it in any direction that you tell it to, and also have the ability to locate someone and drive to that person, or even follow them. Although that's not our immediate goal. Yeah. Cool. So for our technical approach, we want to use basically a Raspberry Pi and a Matrix Creator hat, just like Ray. And then basically build it on some sort of robot platform like the one I have pictured right up there. So the way we want to basically implement it is do beamforming as well, because the Matrix Creator has a microphone array to basically get like an initial direction on where the person is, and then once the robot is essentially pointed in the right direction, we want to have the OpenCV portion take over and then drive directly to the person using computer vision. So we'll do that with the OpenCV library. And then, so our current progress is basically just have Google Assistant running on the Raspberry Pi. So we want to expand that to do the functionality that I described. And then we have just like a basic block diagram right there. The power system could hook up. So, yeah, that's about it. Yep.
I'm Ahmed, and my partner is Hannah, and our project is Healthy Alexa. And basically the goal of Healthy Alexa is so everybody has wearables, or like most people have wearables that they use, such as the Fitbit, or there's a couple other ones that came out that also like the Fitbit, sensor arrays that you wear on your chest, your ankle, headbands, and such. And we wanted to bring that data that those collect into the Alexa, where you would be able to ask Alexa questions such as, hey Alexa, what was my average heart rate over the last 3 hours maybe? Or what is my average activity over the last week, and how does that compare to historically my activity over the last month? And so we hope to answer these questions by collecting the data from the Hexiware and sending it, processing it in such a manner and sending it off to a database somewhere in the cloud, and then having Alexa access from that database. And our technical approach, obviously we'll be collecting the data from the Hexiware, the data such as temperature, humidity, heart rate, gyroscope data, and accelerometer data. And we're going to transmit it over to a Raspberry Pi or mobile device where some of the processing will be done, and store it off on the database onto the cloud. And from the other side, Alexa is going to be able to query an API and query the database, which will let her know what kind of data, like the user will ask a question and Alexa will grab the appropriate data and answer the question. For our results, we've started with some data collection from the Hexiware. Gyro data here, for example, in the image. And we began looking at the literature for the signal analysis, because some of the data might be good in its raw form, such as heart rate, you'd want like the raw data from there, but you can also make inferences from other data, because you don't really want gyroscope data or accelerometer data in its raw form. You want to be able to infer things from that. And from the other end, we've started with some basic Alexa skills. We have a good grasp of that now, and we'll be able to implement whatever we need from Alexa. So next steps will be to decide how we're going to store the data. We're looking into time series databases because obviously we want a lot of historical data, and that's going to be a lot to process through or a lot to store. And so time series databases are optimized for this kind of thing. And options are AWS TimeStream, but I think you might have to pay for that. InfluxDB is a free alternative that we might have to use. And yeah, transferring the data over to the Hexiware, over to the Raspberry Pi from the Hexiware. And that's all we have. Thank you.
Thanks.
Hi, I'm Michael, and my project partner for this project is Sydney, and our project is about an Aware Alexa. So the current problem with Alexa is that usually it's a reactive system instead of a proactive system. It will only usually respond if you give it a command or like you set a reminder or some alarm, then it'll do something. So what we want to do is try to make an Alexa to be more proactive. So let's say the user opens a door, right? You can usually put a motion sensor in it, and you can have Alexa say something, so that's like proactive. But we also want to make it so that it's more, more unique, as in a sense like it can recognize which user has opened the door, things like that. But to do something like this, we need extra sensors with it. So, for example, for the door application, we're thinking about like somehow track user location or like some form of user pattern that we can recognize so that it's able to distinguish a user. So yeah, like I said, our goal is to design Alexa to be aware of its user so that it can predict and perform actions on behalf of the user without having to tell Alexa what to do. And so we will achieve this by collecting data, and the aim of our project is to create an architecture that's simple to use and so that you can practically almost apply it to most applications that you can think of. And so our second goal is to demonstrate this architecture through examples. So like we said, the door example. So this is our technical approach. So what we have is some smart home sensors, and it'll be feeding data to an AWS server. And from there, we create Lambda functions. And a Lambda function is essentially like
basically you can think of it like an if-else statement or if-else event. So if the requirements are met, we just fire an event to an Alexa skill, and depending what the Alexa skill is registered for, it'll perform the necessary action. And because we need external sensors to help distinguish which user, we will also need to use another embedded system. So for example, to keep track of location, we were thinking about using like a Raspberry Pi with Bluetooth, and then we would just grab the RSSI to determine whether a user is near the door or not. Because usually when you leave or open a door, you usually have your phone with you, so from there you can detect the signal strength, and from there you can get the MAC address and figure out which user it is. So our initial results, we've looked and worked on the Alexa skills, and we think we've got a good handle of it. We've also studied some important APIs that we think will be needed, such as the Smart Home API from Alexa, location services, and the SDK and the databases, and also the SmartThings Hub, because for our motion sensor, it requires a Z-Wave compatible device, or you get a hub for it so that it can communicate with Alexa. And those are also RESTful APIs, so from there we can retrieve the statuses of our devices. Next, we're planning to start integrating everything together and see if it actually works.
I am Akash, that's my partner Nat, and our project is time synchronization for ESP over BLE. I think Ray mentioned in his presentation that BLE doesn't have very good system for doing time stamping, which makes it very hard for IoT devices, because a lot of IoT devices use it since due to its power capabilities. So the goal of our project is to establish a publisher-subscriber network over BLE, possibly Wi-Fi, which can help two different devices synchronize their times over a BLE link. The sub-tasks in our projects are, first of all, we want to be able to establish like a link between multiple devices using BLE or Wi-Fi. Primarily, we want to focus on BLE because it is low power and it has not been explored much in academia. And also, second thing is that if you're using Wi-Fi, you always need an APN, and not all Wi-Fi modules provide the capability of them to be used as a hotspot. So if you're using Wi-Fi, you need an APN. Next, we want to explore the best way to timestamp over BLE. Now, the ESP boards that we are using, we are using these boards because they are essentially a Wi-Fi / Bluetooth module. They have a dual-core processor with that's not really efficient, really fast, and they provide. You can use either Bluetooth Classic or BLE. And the next subtask in our project is that we want to quantize the internal time delays in the chip. So basically, you would be a Bluetooth module talking to the processor, getting the time, what are the delay in that inside the chip. And lastly, we want to contrast between a timing that is done through software versus hardware interrupts. So the problem with software interrupts is that the callbacks in those interrupts do not necessarily have the highest priority in this whole stack. However, with hardware, basically you're going down to the lowest level, and you can get very close to the highest priority. So the methods and the technical approach of our project is as follows. So we want to develop an API that using that API, a server can advertise its address, scan the whole network, and create connections with every device in the network. Second is we want to implement the precision time protocol, which was discussed in class, for every link on Bluetooth. Next, possibly we want to include models that estimate the variances, like what's the mean of the delay, what are the variances and what's the spread of your delay. And possibly we'll also look into non-linear methods for time synchronization, like SVM. I think we briefly discussed a paper in class yesterday, and or like shallow neural networks. So what's the current status of our project? We have established a BLE link between two devices, and we are now trying to connect one server to multiple clients. The ESP board actually provides the capability to have like multiple slaves to a master, and that way you can connect like multiple devices. Next is we have also side by side. We are basically we are trying to do both things parallelly, doing this over BLE and doing this over Wi-Fi. So the good thing about ESP is that it has it basically has a library which you can call, and it creates a Wi-Fi mesh between different devices. So the max limit of the Wi-Fi mesh is 16 nodes. We have tested it on 3. We haven't gone beyond that. And lastly, we have already started. We now have the capability to access the hardware interrupts with the hardware timers using both hardware interrupts and software interrupts. So yeah.
This is the last one.
Yeah, that's the last one. Okay. Cool.